This is part 13 of the Module 11 lecture. Everything that I've shown you earlier that we calculated by hand, Excel produces when you use the regression option under the data analysis. So it is conceivable that in the final exam, instead of having you do all these calculations, I may ask you to interpret or conduct the first part of the regression analysis using the output produced by Excel. So here you would see that here's the R-square, here's the standard deviation of the residuals right here. And Excel produces this table called analysis of variance table, and this p-value right here is testing the hypothesis that the model with only the intercept parameter is appropriate versus the model with the parameters, the intercept and the slope parameters. So this p-value is so small that you reject the null hypothesis. So this is telling you that you need both parameters in the model. But if you notice, this p-value is exactly the same as this p-value here, which is the test that the slope is 0. So that's why we didn't bother to explain this, because this is the more meaningful test is right here. All right, so now in this lower table, here is the value of the intercept A, and here is the value of the slope B. And then here's the test statistic for this hypothesis that the slope parameter is 0. But more importantly, here's the p-value for this test. So you see that this p-value is very, very, very small. So you will reject the null hypothesis and then say that the slope is not 0. And here are the confidence interval limits for the slope parameter B, right here. And these are 95% because that's what we told Excel that we wanted. If you are asked for a different confidence level, well, you just change that in the dialog window for the regression. Right, so up to this point, Excel does everything correctly. The next part of the analysis, we have to do it ourselves by hand, use our calculator or Excel to do these calculations, because Excel does not produce what comes next. All right, so the next step is, let's assume that at the top of some mountain, water boils at 206 degrees Fahrenheit. So now we use the sample regression model to calculate what the barometric pressure would be for 206 degrees Fahrenheit, and we want to calculate the corresponding confidence and prediction intervals. All right, and of course interpret them. So using our regression equation, we substitute 206 degrees Fahrenheit into the equation, and then we find that the barometric pressure will be 26.6521 millimeters of mercury. So if we were asked to interpret this value, we would say that when at the top of a mountain, if the water boils at 206 degrees Fahrenheit, the barometric pressure on average or for a single random measurement is expected to be 26.6521 millimeters of mercury. All right, with this prediction, now let's calculate the confidence and prediction intervals. But remember, we need to justify the distribution to be used. So again, using the regression assumptions of that the random errors are independent and normally distributed, and that the standard deviation of the random errors is replaced with the standard deviation of the residuals, then we'll use the t-distribution with 15 degrees of freedom to construct these confidence intervals. Now, to find the critical value for, or that t alpha over 2 for these confidence limits, we'll use table 5 with alpha over 2 and the degrees of freedom of 15. So we find that this t alpha over 2 is 2.131. So with the fact that we know that the t-distribution is correct, and with the t alpha over 2 from the table 5, then we proceed to calculate first the 95% confidence interval. Again, this y hat at x0 is a prediction from the sample regression model, and that's 26.6521. Then we have the t-value, the standard deviation of the residuals, the number of observations, and then this value for at which we want to predict for. That's the temperature, 206, the average of the temperatures, and the sum square of the x's. If you put all these values together, you find that the lower confidence interval limit is 26.5260. And using the same formula, but adding this part to the estimate from the regression equation, we find 26.7782. Now that we have this, we interpret this confidence interval, and we say that the mean of all barometric pressures measured when the water boils at 206 degrees Fahrenheit is between 26.526 millimeters of mercury and 26.778 millimeters of mercury with a 95% confidence level. So this is the confidence interval for the mean of the barometric pressures at 206 degrees Fahrenheit. All right, so the next we calculate the prediction interval, the 95% prediction interval, which is a very similar equation, except that we have this one extra addition of the error of an individual value. So again, putting all the numbers into the equation, we find that the lower limit is 26.1401 and the upper limit is 27.1641. So interpreting this, we say that a random measurement of barometric pressure when water boils at 206 degrees Fahrenheit would be between 26.1401 millimeters of mercury and 27.1641 millimeters of mercury with a 95% confidence level. So if you were at the top of a mountain and when you boil the water and it boils at 206 degrees Fahrenheit, you would expect the atmospheric pressure at that point, when you measure that, to be between these two numbers. All right, so with this, we complete the analysis, but we have one more thing, and that's to verify the assumptions. All right, so here's a graph of the observed values versus the predicted values. The red crosses represent the predicted values, and the black circles represent the observed pressure values for each temperature. And you can see there is a relatively close agreement, except for this value that may be way off. But before we can accept this and all the inferences that we've made so far, we need to then look at the residual plots. All right, so we'll look at the first graph is the standard deviation of the errors versus the predicted values. And again, we see now these values way off. So this compared to the others, so this seems to be an outlier. And then if we look at the band of points, they follow this curve pattern. But when you look at the points, if you think of this as a band that goes like that, that band seems to be of the same width. So that may indicate that the standard deviation of the errors may be constant for all predicted values. Now, when it comes to look at the normal probability plot, then we see a problem. So here, these values of these residuals are not following a normal distribution. So the residuals are not normal. So we're violating the assumption of normality. What's the problem with that? Well, the use of the t-distribution falls apart because we were assuming that the residuals were normal. So our inferences are not valid. And then we look at the residuals versus the temperature, and this is the predictor variable. And here you see very similar pattern as over here, which is this is an outlier, and you see that these points are not a random band of points. There is curvature or some sort of non-linearity between the pressure and the temperature. So again, the assumption that there is a linear dependence, even though the graph looks like there's a good agreement, the residual analysis is telling you, no, there is no a very good agreement. In fact, you don't have a linear relationship, and not only that, your residuals are not normally distributed. So in fact, if we had if we moved on to a more in-depth discussion of regression analysis, we will find that relationship between pressure and temperature is actually exponential. And if you use the logarithm of the let me go to this graph, the logarithm of pressure versus temperature, then you get a straight line. And then when you do the residuals, you find that they are normal and this curve disappears. Even this outlier persists though. So there was a mistake in this measurement. All right, so we will stop here. And our conclusion would be that a simple regression equation for this data is not appropriate, even though on first appearances, it looks like it would be adequate. But that's why the residual analysis is so important. Everything looked fine, but when we actually do the residual diagnostics, we find that we have no normality and the relationship is not linear. So please don't forget, if you do regression analysis, do the residual plots to verify the assumptions. And one more thing, we didn't construct the first graph where we saw the residuals versus the order in which the data was obtained, because that's not given to us, so we cannot do that. All right, so I'll stop here. With this, we finish module 11. And so again, there's these assignments, and look at Wiley plots to see when they are due. And so at this point, you should be able to explain what regression analysis is. You should be able to calculate and interpret the least square estimates of the intercept and the slope, the standard deviation of the errors, and the coefficient of determination. You should be able to perform a test of hypothesis for the slope parameter and calculate this confidence interval and interpret the results. You should be able to explain what a linear correlation is, calculate the correlation coefficient, and test the hypothesis about the correlation parameter and interpret the results. And then you should be able to make predictions using the regression model, calculate the corresponding confidence and prediction intervals and interpret them, and list assumptions regression analysis, and explain how it's verified with residual plots. Right, so with this, we're finished with module 11, and we reach the end of our course. So good luck, and we'll meet again for the final exam.